Welcome back to the Rule Your Pool podcast. This is episode 128, and I am so grateful that you are still listening to this, amazingly. I'm your host, Eric Knight, and I actually got a lot of feedback from the last two episodes, and I figured this would be a good chance to dive a little bit deeper into the same question that I got from multiple people. I had mentioned something in there that piqued interest, and multiple people around the country have been asking about it. So I wanted to dive a little bit deeper into alkalinity's complicated relationship with chlorine. I'd like to talk about two different relationships between chlorine and alkalinity in both directions. The first is how alkalinity levels impact chlorine longevity in outdoor stabilized pools that use CYA. The second is how two primary chlorine types can actually impact alkalinity levels. So without further ado, let's get into it. Episode 128 of the Rule Your Pool podcast.
Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
Kind of funny, on my show notes here, I just have a flow chart of ideas. I have high alkalinity leads to a higher pH ceiling, which leads to a higher pH throughout the course of the week. And that higher pH means that hypochlorite ion will dissociate from cyanuric acid and get burned out by sunlight. Let's take a step back and explain what that means. Cyanuric acid, for those of you who are new to the show, is a chlorine stabilizer. It protects chlorine from being destroyed by sunlight. The UV rays of the sun will destroy chlorine, but chlorine can be protected from sunlight with cyanuric acid. But if chlorine breaks away from cyanuric acid, it's vulnerable once again. So this doesn't apply to indoor pools. This doesn't apply to pools that have no CYA. This phenomenon happens in most residential pools, though, especially pools that have over, I would estimate, about 90 total alkalinity. One of the big questions we get is how to hold chlorine for a week, especially from pool pros that show up once a week. How do you get chlorine to last 7 days? We get a ton of questions about this every single year. And the first thing we say is look at your oxidant demand. Look at the actual chlorine demand. What does it need to destroy? What are the contaminants, non-living and living? What are your metals? Do you have combined chlorine? Have you tested for that? We did an episode with Terry where he brought up you should test for combined chlorine. Amen. I agree. Find out if you have those nitrogen compounds in there. But it's not just chlorine demand that can reduce your chlorine levels. You see, there's a big difference between using chlorine and losing chlorine. We lose chlorine to sunlight if it's not protected by CYA. A lot of people think the hotter the water gets, they need more CYA to hold chlorine. Well, let's expand upon that. That's not technically true because water temperature doesn't have much of an impact at all on how well chlorine stays attached to CYA. There's no correlation there. But what you are seeing is chlorine performing faster. It's getting used up faster because it can work better. It's doing its job at a higher rate. Therefore, it's not going to last as long. Conventional wisdom in the industry came about because of a coincidence that was mistaken for causality. Here's what I mean by that. Pool professionals and homeowners have rightfully observed that in the middle of summer, when it's really sunny and hot, it's harder to hold chlorine for a week. That's absolutely true. But the thought was that you need more CYA to get it to last longer, to get that chlorine to hold for 7 days. What was really going on was slowing down the active chlorine so that it didn't get used up as fast, and therefore you were more likely to have some chlorine still in the water after a week. The problem with that is, yeah, you got some chlorine, but it's slowed. It's slowed down to the point where you're probably behind what you need to be doing in order to prevent issues like algae and other things that could grow and reproduce. You don't want to overstabilize just so that you can have a chlorine reading. Yeah, you want a chlorine reading, don't get me wrong. But what we really want to do is we want to understand what is chlorine getting used up on. Well, here's the other variable that people aren't thinking about. And honestly, I wasn't thinking about it for a while. But let's take a look at the graph. We've talked about this graph. If you open up the Orenda app and you go to the calculator and you tap CYA, there's an underlined hyperlink for cyanuric acid, you will see a graph pop up. You can view this in our website as well. On the left graph, you're looking at a pool with no cyanuric acid. What you're really looking at is a red line crossed with a green line. The red line is the strong killing form of chlorine, hypochlorous acid, and the green line is the much weaker counterpart, hypochlorite ion, OCl-. They are in perfect equilibrium. At about 7.5, they're 50-50, and the lower your pH, the higher the concentration of the good form of chlorine, which means your chlorine is faster, stronger, better, you name it. The chlorine performs better at lower pHs when there's no CYA. So you want to focus in on that red line, that percentage of hypochlorous acid. That's what we're referring to in strength of chlorine. Now, if you look on the right side, the only difference between these two pools is the chart on the right has 30 parts per million of cyanuric acid. And look how dramatically different the lines look. Where's the red line now? It's down by the floor. Now, it's not all bad news. Yes, your hypochlorous acid concentration is very low, but there's no noticeable difference between 7.5 and 8.0. And this is part of the reason why we say it's okay to let your pH on a residential pool get up to 8 or just above 8, as long as your LSI is balanced, if you have cyanuric acid in your pool. Notice we don't say that for indoor pools, because an indoor pool shouldn't have cyanuric acid in it, although there are some arguments that could be made that maybe a very small amount. But I'm going to have Richard Falk on this podcast to discuss that. He wrote a great article about it, and I'm curious to pick his brain. But let's get back to the focus. If there's no CYA, you have to use the chart on the left, because that's what determines the speed of the chlorine. And it's real. It's a real chart. It's published everywhere. What isn't published very often is the chart on the right. And this is where people doubt what we say, but we didn't make it up. We got it from the CMAC, which stands for the Council for the Model Aquatic Health Code with the CDC. It's not our chart. But look at the profound impact that cyanuric acid has. Now you look at that red line at the bottom, you think, oh my gosh, there's almost no chlorine strength. Not quite. Look at the new line at the top. It's a purple line, and that purple line is chlorine that is bound to CYA. So you do have chlorine, and you would test chlorine, no problem. It's in there. But look at the bottom right corner. The yellow and green lines curve up, and at the top, the purple line proportionally curves down. What that's telling you is as the pH rises, hypochlorite ion, the weak form of chlorine, is starting to break away from CYA. It's starting to dissociate. When your pH is going high, in other words, chlorine is breaking away from CYA and getting destroyed by sunlight. This contributes to chlorine demand. I didn't notice this at all on my pool, and I left my pH at the pH ceiling right around 8.02 for most of the summer. I had no problem holding chlorine, but then again, I was chlorinating twice a week, half a gallon each time, so 1 gallon a week. I had no issues. Could I get through 7 days? I don't know. Maybe not. I'm not entirely sure. I didn't try. Maybe that's something for next year. But I do know this much. If the pH gets over about 8.3, enough chlorine starts leaving cyanuric acid that there's a noticeable drop-off in free chlorine levels. So maybe visualize that cyanuric acid is kind of like a floating inner tube with an umbrella on it in the pool. And there's 3 chlorines hanging onto it, and they're in the shade. But the higher the pH goes, the weak form of chlorine, hypochlorite ion, breaks away and says, I don't need this shade anymore, goes out in the sun and gets fried. And you lose that chlorine. That's basically what's happening. So in summary, the higher your pH goes, chlorine leaves cyanuric acid and gets burned out by the sun. Obviously, this doesn't apply to an indoor pool. This doesn't apply to a pool that has no direct sunlight. It does apply to a pool that's outdoors with cyanuric acid. What does that have to do with alkalinity? Well, let me go back to my little flow chart that I had on my show notes. A high alkalinity increases the pH ceiling, which leads to a higher pH over time, and that higher pH means that hypochlorite ion will dissociate from CYA and get burned out by sunlight. So that high alkalinity sets the table for having a higher pH ceiling, So that when you're gone, pool pros listening, I don't know, day 5, 6, 7, depending on the aeration, depending on other factors in the pool, whether or not you have a auto cover or not, that pH is going to get up there. And when that pH gets up there, you could be losing a lot of chlorine to sunlight because that chlorine just doesn't want to stay connected to CYA. Pretty interesting. So who knew that alkalinity actually had something to do with chlorine demand, especially in the summertime? So what's the answer? Well, keep a lower pH ceiling. It ties really nicely with everything else that we teach. We color-coded our app so that if your pH ceiling is over 8.3, it turns purple. Yes, that means that it's likely going to form scale, but you can also use it in this sense. Try to have a pH ceiling in the green. If you do, you're probably going to be able to hold chlorine longer, at least from that variable. Again, there's oxygen demand and all these other factors, but at least you can take that factor and minimize it. Do you really need 100 alkalinity in a liquid chlorine or cal hypo pool or a salt pool? Probably not. But you do need to make sure that your free chlorine to cyanuric acid ratio is balanced and you have sufficient sanitation in that water. Water needs to be safe, clean, and clear. That is a priority. So don't have too much alkalinity because you're going to probably lose some chlorine to sunlight if you do that. So that's the first thing. The second relationship goes the other way. This was the question that was brought up from my last episode, 127, where I was talking about what I did in my pool this year, pretty much breaking every conventional rule that we have in this industry on purpose. The question that came up was, how did your alkalinity stay there? Why did it stay there? I wasn't adding bicarb. I was vacuuming. I was losing water. And I did have some torrential rain. By all accounts, my alkalinity should have gone down in the summertime. But it didn't. It has consistently been between 5 and 6 drops on a Taylor kit, which means it's between 50 and 60 total alkalinity. Here's what I think has happened. We've talked before about pools that use CO2 systems. Pools that use CO2 systems tend to have alkalinity that rises. The reason for that is they are not adding acid very often. If your pool is on liquid chlorine, sodium hypochlorite, or cal hypo, calcium hypochlorite, there are some excess hydroxides in those chlorines. And those hydroxides will accumulate over time because you're not using acid, and they will contribute to total alkalinity. Your alkalinity goes up because of the chlorine. It's not because of the CO2. The CO2 just precludes you from using the acid. And just a quick crash course. Actually, you know what? I'm going to see if I can do this in one breath just to make sure I don't spiderweb too much. If you want to lower your pH, you have to have more dissolved CO2 in your water. So when you just inject CO2, that's no problem. You create something called carbonic acid, which is H2CO3. That's H2O plus CO2. But if you want to create carbonic acid with muriatic acid, you actually have to burn through bicarbonate alkalinity by adding a hydrogen to it. It converts HCO3 minus to H2CO3 carbonic acid. That's how you get dissolved CO2, and therefore acid reduces both alkalinity and pH at the same time. Nailed it. That's what we're dealing with. You would never notice these excess hydroxides in these chlorines if you're using acid because it's a very small amount, but it accumulates over time, and that can actually cause an increase. Well, what did I do in my pool? I wasn't using CO2, but I also wasn't using acid. I didn't touch acid since May 14th. Coincidentally, today is Halloween. It's October 31st, and I just did a Facebook Live about an hour ago. I added 50 pounds of calcium to prepare my water for the winter. It's getting colder here. Today was the first day I added acid since May 14th. It was 12 ounces. And I put it into the startup barrel with 50 pounds of calcium and 5 ounces of SC1000. So I went the whole summer without adding acid. And because I wasn't adding acid, my chlorine was increasing my alkalinity because of those hydroxides. So here's how it works. Any type of chlorine that you put in water, when it dissolves, you're going to get hypochlorous acid, HOCl. And let's say there's no CYA in there, that will dissociate based on pH with hypochlorite ion. We just drove on this in the last section here. That's OCl minus. Well, when HOCl oxidizes something, it steals an electron from something and it gives the oxygen, or it swaps. I don't know the technical way to say that. If you're a chemist and you want to email me, podcast@orendatech.com. I'd like more clarity on the verbiage there. But essentially, HOCl becomes HCl, hydrochloric acid. And hydrochloric acid should sound familiar to you because that's muriatic acid. Muriatic acid is technically a 31.45% or less concentration of hydrochloric acid. But anyways, it creates its own acid. So whatever chlorine type I have, I'm going to have some muriatic acid created as a byproduct when chlorine does its job. This is why liquid chlorine and Cal Hypo, over time, are relatively neutral pH chlorines. But the product immediately when you put it in, they have high pHs. I think Cal Hypo is like 10.5 to 11 or so, and liquid chlorine is about 13 to 13.5 pH. So the products are high pH, but when you put them in the water, that hydrochloric acid neutralizes most of that hydroxide. So when you put liquid bleach in the pool, sodium hypochlorite, the byproduct is going to be sodium hydroxide, NaOH, and that has a very high pH of about 13. The hydrochloric acid, after chlorine kills, is going to neutralize most of that, but not all of it. And it's that little bit that it doesn't neutralize that accumulates and contributes to total alkalinity. Kind of cool, right? The same thing happens with Cal Hypo. Instead of sodium hydroxide, it's calcium hydroxide, which also has a very high pH. And the HCl, once chlorine does its thing, neutralizes most of that, but not all of it. And that little excess of calcium hydroxide contributes to total alkalinity. So if you have a commercial pool CO2 system, those little excesses of hydroxides will add to your total alkalinity over time. And in my case, I just didn't use acid. I would not have noticed the benefits of this had I used acid each week or even once a month. Would have probably been plenty to neutralize it. But because I didn't, the chlorine increased my alkalinity gradually. My alkalinity stayed remarkably stable. I think it could do the same for you. So anyways, that is the two relationships. High alkalinity will cause a higher pH ceiling, which will mean that more chlorine will leave CYA and get burned out by sunlight. So it increases chlorine demand in that way. Kind of an indirect relationship, but a real one. And the other way around, liquid chlorine and Cal Hypo, without acid being used, can increase your alkalinity levels. I think I covered these pretty well. I hope that explains what was going on and answers all of your questions. For those of you who did reach out, thank you so much. And thank you for continuing to listen to this. I do find it amazing that our audience continues to grow, and I'm so grateful for all of you investing your time with us. If you have questions, my email is podcast@orendatech.com. That's Orenda, TECH.com. The website, or the help center, I should say, is ask.orendatech.com. It means a lot to me that you're still listening to this podcast. We did not think it would go this long. I thought it would probably go, I don't know, less than a year. Get the information out, talk about each blog. Maybe we would run out of ideas. That is not the case, and it's because of you. I've been getting so many good ideas and great questions from our listening audience, so thank you for that. I've got some really cool guests lined up. They're not scheduled yet because we got to figure out the fall schedule, but some really cool people that will be on this podcast to continue to add value in ways that you may not think. It's not all about pool chemistry, but it is about the well-being of all of our customers. Whether you're a homeowner or a pool pro, we care about you. We love you. Thank you. And sorry for the music. I'm going to do less of that. Anyway, that's all I have for episode 128 of the Rule Your Pool podcast. I'm Eric Knight with Orenda. Until next time, you're the best. Thanks.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.